we call chromatography. So as I've told you, this is just a supplement to the one that we have already made available with regards doon sa recorded video, the materials that are based from UP Los Baños. So liquid chrome. So we could say liquid chrome is really the chromatography that was performed by Tisuet when it was first introduced, when the concept was first introduced. Because you have the solvent that push the plant extract towards the mobile phase. Okay, so in liquid chromatography, the mobile phase is a liquid. It's an older technique than GC, but GC became popular first, okay, in the 1950s and 1960s compared to LC. But right now, LC is the most dominant. I think 85% of all chemicals can be analyzed by LC. Okay, and it started to even replace the GC now in its more traditional application. So if you're going to look at the number of publications, especially from the 1990, so it overlaps, okay, the number of papers that was developed or that was reported for LC method. Okay, so if you're going to look at the typical parts or diagram of an HPLC, this is what you see. Okay, so you will have here the pressure, the back pressure. Okay, so there's a lot of things, but everything starts with what? The pump. So what the pump do, it will push the solvent towards the system, and the solvent will pass through a filter. So when you inject your sample, so the solvent will carry the sample through the column and then go into the what we call detector. Okay, so there are several advantages of LC compared to GC. We will going to talk GC when we resume our class after your 1 week break. Okay, so some of the advantages are listed here. So when LC can be applied to the separation of compound that is soluble in a liquid phase. So the requirements for the LC, if you can dissolve your compound or your chemical in a liquid solvent, you can do LC. Okay, so LC is more useful usually in the separation of the biological compounds, synthetic or natural polymers, and inorganic compounds. Now, liquid mobile phase also allow LC to be used at lower temperature than required by GC, because GC works on what? Gas phase. So usually if you're in the gas phase, you're working at a higher temperature. So LC is better suited than GC for separating compounds that may be thermally labile. So if your compound is sensitive to temperature, you cannot utilize GC. LC is the more qualified one. Okay, and then another thing that we can look at it is the retention of the solute in LC depends on their interaction with both the mobile phase and the stationary phase. Okay, the GC basis for what we call separation is volatility and interaction with the stationary phase. They don't usually interact with the mobile phase. The mobile phase of GC is what? Inert gas. So what the mobile phase do for GC, they just carry the sample, but in LC, okay, depending on the solvent that you have, your mobile phase can interact with the sample that you are separating, or the compounds that you're separating within a sample. So we could say LC has more flexibility in optimization. You can change either the stationary phase or mobile phase. In GC, it's just, okay, the stationary phase. Okay, And another example that another advantage that we could say is this, what we call non-destructive LC detectors. What does it mean? Anyone? What does non-destructive mean? Non-destructive detectors. Is it the first time you hear the word? Anyone? So ayaw? No. You're ready for the break. So when we're talking about non-destructive, you can recover your sample. So once it was the detector, it passed through the detector, you can recover your sample for further use. But if it's destructive, it's destroyed. So when it passed through the detectors, they're gone. You cannot use it anymore. But the LC, sometimes you can just collect them. If you see the pig, okay, I can collect with that one. In fact, one way that they do collecting some of these compound is using the LC, the one that they use in large scale. Okay. Now the disadvantage of LC compared to GC is GC usually is what? They have broad peaks compared to, I mean, LC has broad peaks compared to GC. GC, their peaks are really what we call sharp. Now, the band broadening that we have discussed last time, this is just due to the larger diffusion coefficients of solutes in gases versus in liquids. So that's the advantages and disadvantages of LC compared to GC. Okay, so we have a low and a high performance liquid chromatography. So when we're talking about HPLC, the feeder is for performance, not pressure. Okay, there's always a misconception. Even when I was in undergrad, I thought the feeder is pressure. Okay, it's really what we call the performance. And many types of the LC are available based on the different stationary phase and mobile phase interaction. And you could say each type may be further characterized based on its overall efficiency or performance. So at the end of our lecture today, if you're given some compounds in a sample to be separated, you should be able to know what type of LC are you going to use and what type of detector are you going to use. Okay. So we start with the molecular mass. So when we have the so-called low molecular weight, or what we call small molecules, so these are the things that you use. Okay. And the first way for you to separate or classify them is in terms of their solubility. Okay, so you can have those that are soluble in organic compounds and those that are soluble in water. Okay, so those who are soluble in organic compound, if they're so non-polar, what you usually have there is what we call the normal phase. Okay, and this normal phase is based on the absorption or bonded interaction. Now, as the polarity increases, you can have this so-called reverse phase. We're going to talk about this. Okay. And as we go to the aprotic solvent, you can have this gel formation using small molecules. Now, if you have water-soluble compound, if it's the non-ionic, you can have the reverse phase. If it's ionic, then you have to use the so-called ion exchange. Okay. Now, in big molecules, usually you have the size exclusion and the size, size exclusion. One is gel formation and the other one is gel filtration. Okay. So, usually you could say this involves what? High molecular weight. Ano yung mga compound na high molecular weight? Anyone? Now, what do you think is the difference between the gel formation and the gel filtration? Ano yung nagpapaiba sa kanila? Okay, so usually if you have what we call big molecules. These are polymers, biomolecules. So what makes the gel formation different from gel filtration? Sige nga. If you're paying attention. What do you think is the main difference between the two? They're both size exclusion. Okay. But when does gel filtration is used and when does gel formation use? Anyone? Wala.
Or organic salt, organic compounds po yung
Okay, very good. So if you have organic molecule, okay, or organic solvent, the term that you use there is gel formation. But if you have aqueous solvent or water, the term that you use there for size exclusion is gel filtration. Okay, so that's a very good question in what? A true or false question? Okay. And if you have ionic compound that high molecular weight, so you have what we call the ion exchange or the reverse phase. Okay. Now, let's try to compare the so-called high performance versus low performance liquid chrome. Okay. So when we're talking about low performance liquid chrome, these are the ones that use large and non-rigid support materials. So the particles that you have there are usually 40 micron in diameter. Now the problem with this one, they have the poor system efficiencies and large plate height. Okay, and this type of system has the following characteristic. They have broad peaks, they have poor LOD, they have long separation times, and the column can tolerate what we call low operating pressure. So we could say the performance is synonymous to the pressure. Okay, so if we have what we call a low performance liquid chromatography, what we really have there is sometimes the absence of pump. Minsan walang pump. Nag-aano lang sila. Yung tawag dito is maybe gravity. So if you're going to look at the difference in the peak, mas masyadong broaden yung low performance. Kasi walang natutulak. There's no pressure. There's no pump. Okay, that build pressure to push your sample to the column. Okay, so maybe we can include here the one that you use in organic chemistry, right? Gumawa ba kayo nito? Nag-hands-on ba kayo nito? So as you could see here, there's no pump. Okay? So maybe yung ginawa nilang, yung summer, ano yung tinawag nila summer? I forgot that thing. I was already there in the Philippines when they held that thing, but I arrived during the last week, so I wasn't able to go to Los Baños to do that. So this is, we could say, yeah, yung bridge, summer bridge, some sort of. So here, wala talaga silang pump. Okay? So ang ginagawa dito, it's just movement by gravity. So you just add what we call the solvent, and usually the gravity would build pressure and it push down your sample there. So that's the low performance. So yes, samples usually applied directly to the top of the column, and detection is by the fraction collection with later analysis of each fraction. We do that in LB. I have experience using this for my MS thesis there in Los Baños. Okay, yung tinatawag nating gel filtration. Fractionation ang tawag namin. Now, there are advantages of this one, especially for a school like UP Los Baños. Okay, it's low cost, it has simple system requirements, it's popular in sample purification. That's why it's mainly used in natural products. And usually they use it for cleanup. So if you want to analyze something, you want to remove some of the other components to improve the matrix, you're going to use this thing. Okay, sample cleanup. and then you use it in some application. Now, this is not common because of low efficiency, long analysis time, and poor limits of detection. But sa school na gaya natin, we have to use this thing. Okay? Now, when we're talking about high performance, so these are the one that uses small, uniform, rigid support material. Particles is less than 40 micron in diameter, and usually it's 3 to 10 micron in practice. It is a good system efficiencies and small plate height. So such system has the following characteristics. It has a narrow peak, it has a low limits of detection, short separation time, columns can tolerate high operating pressure and power, a faster flow rate. So usually, okay, if you have a good pressure, so depending on the flow rate, you can have what we call a shorter time. So this is an example of the separation of sugar. I experienced doing that in the old HPLC that we have there. I don't know if it's still what we call there. Nakapunta na ba kayo yung mga nasa LB? Have you seen the instrument there in the IC class? Have you already seen the
Not yet po,
instrument there?
sir.
Hindi pa? Wala. Sobra naman kayo. Meron naman kahit pa paano. Kayo talaga. Okay? Meron yung LCMS dyan sa Los Baños campus eh. Kayo talaga. So, this is, we could say, the simplest schematic diagram for an LC system. So you have the solvent reservoir, okay? And the solvent reservoir is introduced to the system by the pump, okay? So once you inject the sample, the solvent will go with the sample there. It will going to be pushed by the pump. And as I told you, the column is what? The heart of chromatography, because that's where separation takes place. So once they are separated, there are different types of detector that we're going to tackle later on, okay? And then there's a readout system, and in most of the detector, you can recover the sample, the separated components of your sample. That's a good thing, okay? For HPLC. So if you're going to look with HPLC, usually you have a high operating pressure. So you need it for the mobile phase to be delivered to the system. Now the sample applied using closed system, you have an injection valve, and then you have a detection uses a flow through detector. So if you're going to look at this, there are different solvent bottles. So maybe tomorrow when I go to the lab, I'll show you HPLC system, so you will see, okay? And then there's some valve, so there's a pump that's going to push that thing, okay? So some will go to the waste, and then most of them will go to a filter, and then a back pressure regulator, and then it will go to the injector port. So that's where you introduce your sample. So once you introduce your sample, okay, the solvent will carry your sample through the column. But even before it goes to the mobile or to the stationary phase, there's already an interaction of your sample with the mobile phase. Okay, and column where separation takes place, and then one by one, they're going to be detected by the detector. So that's how an HPLC system looks like. Okay. So the advantage that you have for an HPLC pass analysis time, ease of automation, good limit of detection, preferred choice of for analytical application, and popular for purification port. Now the disadvantage is mahal, okay, and it has a lower sample capacity. Hindi gaya noon sa low pressure chromatography or liquid chromatography. So again, This is your schematic diagram. When I was a student, ito yung very popular sa amin noon. Draw the schematic diagram of LC system. So maybe in the board exam, you will be given like a drawing like this or just a box, and you are asked what are the parts of the what we call LC or GC system. Okay. Now, illusion. So when you do the separation already, so there's what we call an interaction between the mobile phase and the stationary phase. So once they are separated, okay, you're going to have what we call the illusion. So the illusion, we could say, depends on the interaction of your compound or the components of your sample with both the stationary phase and the mobile phase. So the one that will interact more with the mobile phase will elute what? In short time or longer time? Alin yung unang mag-elute? Yung mas malakas yung interaction sa stationary phase or less interaction sa stationary phase? So usually, if we're going to look at it, if there is more interaction between your component, okay, or sample with the stationary phase, they will elute later. They will stay longer. Okay. Or if they have the component that you have a strong interaction with the mobile phase, they will elute faster. So meron tayong tinatawag na term na strong mobile phase. So this is solvent that elutes solute from the column. So they have a small capacity factor. So this one is what we call too fast. How are you going to make it slower? Anyone? In practical question that needs to be answered practically. Oh no, my internet is unstable. Nawawala ako, no? So what do we do? If we want the separation to be better, anong gagawin natin? Isa lang ang gagawin dyan. Anong i-adjust natin? Masyadong mabilis, masyadong dikit-dikit. What will I adjust? We're going to adjust the flow rate. Anong gagawin natin sa flow rate? Make it bigger or higher or make it lower? Pabilisin? Pag pinabilisin natin, lalong mabilis yung pag ano yan. So if let's say the flow rate here is 1 ml per minute, if you're going to make it 2 ml per minute, so ang mangyari yan, dito pa lang, labas na sila. Okay, but if we're going to make it 0.5 ml per minute, so most likely madodoble yung paglabas niya. Okay? So bababaan natin. Or we could say, pababagalin natin. Tama ba? Okay? Hindi na kasi ako nagagamit ng Filipino words. Okay? We'll make it slower. So usually a polar solvent will be a strong mobile phase for a column containing a polar stationary phase. So you will have a strong mobile phase if it is very similar to the stationary phase in its intermolecular interaction. Okay. Now, we can also look at the illusion. Okay. Let's say, so this is the strong mobile phase. If we're going to use a weak mobile phase, what will happen? The solvent slowly elutes solute from the column. So there's what we call the high solute retention or a large capacity factor. Okay, so remember the ideal capacity factor, not so low, not so high, but the one in between. Okay, kasi pag masyadong matagal or masyadong mataas yung capacity factor, mabagal yung elution. So you have a weak mobile phase. It occurs if the mobile phase is very different from the stationary phase in its intermolecular interactions with the solute. So a non-polar solvent would be a weak mobile phase for a column containing a polar stationary phase. So if you're going to look at here, it's a slow, the elution is slow. If 20 minutes, you're going to see the compounds in the mixture. However, whether you have a strong or weak mobile phase, it still depends on the stationary phase. So this is the advantage of LC, because in GC, it's all stationary phase. Your sample doesn't interact with the mobile phase because your mobile phase is an inert gas carrier. Okay, so hexane is a weak mobile phase on a polar stationary phase, but a strong mobile phase on a non-polar stationary phase. Okay, and maybe similar to GC, the solute or the component that you are separating, it can be eluted from a column by using either a constant column conditions or a gradient elution. So we have here isocratic versus gradient elution. Okay, so the difference between the two, isocratic, you have a composition of the mobile phase that is the same all throughout the runs. Gradient elution, the composition of the mobile phase changes. Okay, so isocratic elution uses a constant mobile phase composition to elute the solute. It's simple, it's inexpensive, but unfortunately, if you use that, it's difficult to elute all solute with good resolution in a reasonable amount of time, leading you to the so-called general elution problem. Okay, so you have this thing, general elution problem, and it's a problem that is commonly found in what we call chromatography, and later on we will discuss this so-called general elution problem. Okay, so when you have an isocratic elution, sometimes it will take you a longer time to what we call separate all the components. And in doing so, you have to make sure what is the best solvent to separate certain type of compounds that are present in your sample. Okay, so you need to identify the solvent composition to obtain the optimal separation. And it's so hard in isocratic because you just have the same composition all throughout. Okay, now, unlike the isocratic, okay, the gradient elution, on the other hand, we could say it changed composition all throughout. Now in GC, you can also have isocratic and gradient elution. But it's not the solvent, it is something to do with what? Ano yung binabago natin pag GC? Anyone? Pag sinabi natin isocratic condition, itong factor na to, it's just the same. Pag sinabing gradient, itong factor na to is just the same. Okay? What do you think is that? It's either of them. Usually it is what? Ano yung main difference ng GC sa LC? Ito. In LC, okay, you change the composition of the mobile phases, but as I have told you, the composition of your stationary phase uniform. Okay, both in LC and in GC. Now, the gas that is your carrier in GC, it will not interact. So the only thing that you're going to what we call change there is the temperature. Why? What's the basis of the separation in GC? Volatility. So some compound, okay, they have different volatility based on the temperature that they have. Some will volatilize at higher temperature compared to the other. So by changing the temperature, you're separating them. Compare it's just maintaining the same temperature. Kuha ba lahat? Okay? That's why you don't call that illusion there. What you call there is just an isocratic and a gradient thing. And I think the one that they call there is temperature programming. You will know about it when we go to GC. Okay? So if the HPLC has the solvent programming, the GC has the temperature programming. So usually the technique that they have going from a weak mobile phase to a strong one. And they assign the weak mobile phase to the solvent A and the strong mobile phase to solvent B. And what they do, okay, the solvent B composition would increase after a certain time and then maintain a constant composition of the solvent. But all throughout the line, the run, the solvent composition changes. That's why it's called gradient. Okay, so try to imagine if you have a gradient illusion like this one. That's 47 minutes. Now imagine if you do this in isocratic. It might be longer, or if you're going to run it at that time, some of the components will not show up. Okay, so you might see here, the composition here changes during the time of the run. Okay, so this is the advantage of what we call the gradient illusion compared to the isocratic. Now, there are several things that you need to take into consideration in choosing a mobile phase for the LC. You have to consider some of these, what we call factors. The type of stationary phase that you're going to use, so determine what will be a strong or a weak mobile phase. Are you going to use a polar or a non-polar column? Okay. And then you have to look at the solubility of the solute. You don't want your component to precipitate, okay, with a certain solvent. It happens. It will clog your system. So you want to make sure that the solvent that you use, okay, the component that you're separating is soluble on that what we call solvent. Especially you have 2 or more solvents. Okay. Now you're going to look at the viscosity of the mobile phase. What happened if your mobile phase is viscous? What happened to the pressure? If the mobile phase is viscous, what do you think happened to the pressure? Or what do you think happened to the pump? If the mobile phase is viscous, you're going to need the pump to work harder. You're going to need a higher pressure because it's viscous, right? Just imagine the syrup. Viscosity is what? Resistance to flow, right? It is what we call the resistance to flow. And then the type of detector that you're going to use and the solvent background signal. We're going to talk about the different, what we call detector, although we already talked some of them in the recorded slide. The purity of the solvents, you have to take that into consideration, and the miscibility of the solvent. So sometimes they're not miscible. Okay, so if they're not miscible, so what will happen? You have 2 components. You have a mixture serving as your mobile phase, and it's not good. Okay, sometimes that alone will show a peak out of the system. So if you're going to look at the selection of the mobile phase for a particular LC application, it can be done by using this table. So you're just going to look like the polarity index, the viscosity, okay, the eluent strength. So this is one way for you to determine, okay, what way they going to what we call work. Okay, so we go now to the what we call types of liquid flow. So we're going to classify the LC techniques according to the method of solute separation. So we have adsorption, partition, ion exchange, affinity chromatography, and size exclusion. Now, if we're going to look at this, most of the things that we're going to talk is between these two. This one, adsorption, okay, and the one that is what we call partition. That's really the basic thing, the two most basic thing that is being utilized in an LCM, an LC system. Okay, but we're going to discuss the other one. So when we're talking about adsorption, okay, so try imagine this as the one that is stick to the surface. So if you're going to look at this, the one that sticks to the surface, so if you have a pie, it is the one that will hit your face because your face is the surface. Okay. So it separates the solutes based on their absorption to underivatized solid particles. So this is similar to gas solid chromatography in that the same material is used as both the stationary phase and support material. So here, okay, if you're going to look at the blue thing here, it is going to be absorbed on the surface. Okay. So the advantage of this is to retain and separate some compounds that cannot be separated by other methods, especially in organic chemistry, you encounter the so-called isomers. So isomers, they usually have what? Almost the same property. They have the same chemical composition or chemical formula. The only thing that they're different is the way they are arranged. Now, the disadvantage of this is it absorbs your compound, okay? It can retain it for a while. So there's a very strong retention of some solutes. And there's this absorption also, they can cause reaction. I mean, your compound that you separated cause reaction with the support material or the stationary phase that you have. So it may cause catalytic changes in your solute. The solid support may have a range of chemical and physical environment that leads to non-symmetrical fixed and variable retention time. So remember, as I've told you, absorption is just like the pie stick to your face. Okay. So if you're going to look at this, you look at the different, we could say adsorbent. So this is the solid support. So it can either be what we call for polar or non-polar application. Okay. Silica, that's the common absorbent. Surface type of it is slightly acidic, so it can be used for most basic compounds. The alumina is slightly basic, okay? So it can be used for mostly acidic compounds. Now you can use a charcoal, it's non-polar, so it is used for non-polar compounds. Okay, now fluorosil, this is strongly acidic, so you can have what we call the basic compound. Now you have polyamide, so this is a basic. You can use it for phenols and aromatic compounds and other stuff that you have like diatomaceous spirit, clay, kilsugar, saline, they're regularly non-polar, and you can use it for polar compounds. Now, If you have polar support, you use silica and alumina. Okay, and in a polar support, your weak mobile phase is a non-polar solvent, and the strong mobile phase is a polar solvent. Now for the other one, the non-polar is the other way around. The weak mobile phase is a polar, and the strong mobile phase is non-polar. Where do we use absorption LC? Purification of synthetic organic compound from organic mixture. So usually separation of geometrical isomers, the ortho, meta, para. You're familiar with that? And the cis and trans, same position or opposite position compound. Okay. Now, how does the other one what we call compare to the absorption? So if absorption, you have a pie that stick to your face. In a partition, it's just like you're eating the pie. It doesn't stick to your face. It doesn't stick to the surface. So from the word partition, what happened? Your solute is separated, okay, wherein the component partition between the mobile phase and the stationary phase. And usually the stationary phase that you have there, it's a liquid stationary phase, but it's coated on a solid support. Okay, and the solid support that you have here is just similar to what we have discussed. But at least in the absorption, it's just a solid support and the stationary phase. Here, okay, you have a solid support and some other material coated on that solid support. I hope you see the difference, okay? So you have a silica, you originally involved coating the support with some liquid stationary phase that was not readily soluble in the mobile phase. And there's two types of this partition, the normal phase and the reverse phase. Okay? And between the two, this is the one that is more commonly used. My experience is I use it, what we call the reverse phase. Now you may ask, why do we call one normal and the other one reverse phase? So when we have a normal phase, it just has something to do with the stationary phase. So if you have a normal phase, your stationary phase is polar. Okay? So the NPLC column strongly retains polar compound kasi polar yung stationary phase. So you have here a weak mobile phase that is non-polar, usually not an organic solvent, and a strong mobile phase that is polar, which can be water or methanol. Okay, and the stationary phase must have low miscibility with the mobile phase, so the stationary phase is not dissolved in the column. So these are some of the stationary phase that they have: the cyanopropyl, aminopropyl, and the N-propyl diethylamine. So this is the one that is coated with the silica. So yung silica nyo dyan, yung SI. Tapos naka-coat yan. Yung cyanopropyl, okay, aminopropyl, at saka iba pa. So since you have CN, NH2, okay, you have there a polar stationary phase. And the common application for this one, purification of synthetic organic and inorganic compounds from reaction mixture. General purpose separation of polar, non-polar compounds when the sample is in a non-polar solvent. So alin yung unang nalabas sa NPC? Yung polar molecules or non-polar molecules? Huh? So let's say I have the thing in NPLC. I have this, and then the two ring, and then the benzene. So alin yung unang mag-elute? Yun nga. Yan yung mga tanong na pwedeng tanungin hanggang board exam. So, anong unang lalabas? Ang unang lalabas, ang polar or non-polar? Isip-isip. So, ang ano dan, 1 ring, 3 rings. So, 50-50% hula pag hindi alam. So, remember, ano yung stationary phase? Polar or non-polar? Yung stationary phase mo sa normal phase is polar. So, that means, okay, yung solvent mo, if you're going to look at it, the solvent that you have there can be a mixture of the two. So if that happen, ang unang lalabas dyan, okay, ay yung pinaka non-polar. Okay? Kasi ang mag-i-interact doon sa polar stationary phase is yung mas polar. Now, all of them are non-polar, right? But there's a degree of non-polarity for them. So, alin yung pinaka non-polar dito? Yung 3 rings. Am I right? Agree ba kayo ng pinaka non-polar dito ay yung 3 rings? 3-membered rings? That's how you call it. What do you call this? Is this anthracene? Then the second one is naphthalene. Am I right? So, ang unang lalabas ito. Ang huling lalabas ay yung 1 ring. Because it will stay longer doon sa stationary phase. Okay? Now, if you have the reverse phase, it's the reverse. You have a non-polar stationary phase. And usually, you have a polar mobile phase. Okay? So a reverse phase chromatography, it is a non-polar stationary phase. So there's a reverse of polarity to that of the normal phase, LC. And it retains the non-polar compound most strongly. And usually the one that you use here, water as the polar, and then methanol or acetonitrile as the non-polar. So if you're going to compare with them, ito siguro yung summary. Yung dalawa. Okay? And if you're going to look at the component of the stationary phase, so you can see they are really non-polar. They're almost made up of what? Hydrocarbons, right? Commonly that you use is a C18 and a C8. I use C18 in my grad school, and then I have a C18 and a C8 in my lab. Okay, so if we're going to look at this reverse phase, they are the most popular one. Karamihan ng analysis, they use this what we call method. The separation of a wide variety of non-polar and polar solute. So the popularity there is your weak mobile phase is a polar solvent, which is water. And it's ideal for the separation of solute in an aqueous sample, such as biological systems. So if we're going to go here, if you have the what we call normal phase chromatography, so you have a low polarity here of the mobile phase. Okay? So, tingnan nyo yung difference ng dalawa. CBA. So, this is C being the what? The most non-polar. Okay? If you're going to look at the solute polarities, A is the most polar compared to B and C. So if it's a normal phase, the least polar, that's the one that comes out first. If it's a reverse phase, the most polar come out first because the least polar or the most non-polar interact more with the stationary phase, which is non-polar. Okay ba yun? Kaya nyo sumagot ng question? Kung meron kang NPLC or RPLC, alin yung unang mag-e-elute, alin yung huling mag-e-elute. Now, reverse phase is most, I think most of the papers that I read is always have reverse phase liquid chrome. The purification of biological and organic compounds present in aqueous solution, pharmaceutical analysis, protein and peptide mapping, analysis of soil and water samples, and clinical analysis of blood and urine. Okay, so example that you have here is this one. Analysis of patient blood serum for the presence of a drug during the clinical trial. So if you end up in the industry, yan yung gagawin nyo. And the good thing, they're automated. Okay? So question within the two, because those are the most important one. The rest, iaano ko na lang, shorten ko na lang, because they were already discussed in the lecture, the recorded lecture. So the other thing that we have is the ion exchange chromatography. So if you have an ion exchange, you can have the cation in the solid support or the anion in the solid support. And the interaction that they have is the charge. Opposite charges attract. Okay? So in ion exchange chromatography, it separates by their absorption into a support containing fixed charges on its surface. So what you have is a high concentration of competing ion often added to the mobile phase to elute the analytes from the column. So what it do, it just exchanges, okay, whatever solid support that you have here. You have here usually a resin. So if you have an anion exchange resin, it will bind with a cation. Okay. So there are two general types of this solid support or stationary phase. One is a cation exchanger. So it has a fixed negatively charged that used to separate charge, positive charge ion. And then you have an anion exchanger that has a positively fixed charge or positively charged group and separate negatively charged. So these are the functional group that they have. Sulfonic acid, carboxylic acid, carboxyl methyl. So what you do here, you remove the H plus there and it will be replaced by another cation, positively charged ion. Now for this one, you remove the negatively charged and it's going to be replaced by another negatively charged. Okay. So you can use some stationary phase support material here. Okay, like the crosslink polystyrene resin, carbohydrate-based resin, or the silica support resin if you're going to perform high performance separations of biological molecules. Okay, so if you're going to have here, this is the cation resin, the cation exchange and an ion exchange resins that you use. Now, another thing that you need to consider here is the change in the pH. Okay, so a solvent that has a pH with decreased ionization of the analyte or stationary phase can affect, okay, the nature of the separation that you have. So factors that may affect the mobile phase strength, the mobile phase pH, okay, the mobile phase concentration of the competing ion and the type of the competing ion. So when you say type, the positive one, positive two, okay, so it will have an effect on the separation. Now, this is commonly used for ions or ionic compounds if you want to separate them. And amino acid, proteins, peptide, nucleic acids, you can separate them because they have some charges. And you can play around with the charges that you want to change in the pH. Okay? Now, affinity chrome, you take advantage on what? A specific interaction. Okay, so maybe it can be in terms of an enzyme reacting with a substrate, okay, or an antigen reacting with a thing that will react with it. So the way that you have in affinity chromatography, you're going to put or immobilize your biological molecules as the stationary phase. And it will bind with a specific substrate. Okay, so binding of an enzyme with the substrates or a hormone immobilize one of a pair of interacting molecules into a solid support or immobilized molecule on a column that is referred to as affinity ligand. So the experience that I have here, I isolate lectin from I don't know, you know, sea cucumber. And the solid support that I have there is pet-to-win. So it will bind with the pet-to-win. Okay. So you can have an antibodies reacting with, interacting with antigen. You have an inhibitor or substrates with enzymes and nucleic acid with complementary nucleic acid. So the one that I talked to you, that's lectin, is a glycoprotein. So they interact with a certain pet-to-win material. So it binds to that, the lectin binds with that pet-to-win. Okay. Now, you don't need it to be what we call biological in nature. The pet-to-win is not biological in nature. It is what we call chemical in nature. So this is very, we could say, selective. And that selectivity make it what? A very popular use in the biological component. Okay. And you can manipulate or modify the condition as easy as just changing the pH, because at different pH, sometimes the activity of the stuff that you're trying to separate will change. Okay, it can change the binding constant or replace the solute by addition of an agent which compete for the solute sites on the column. Okay, so the common application that you have here, separation or purification of biological molecules, isolation of cells and viruses, purification of nucleic acid, clinical and biological sample analysis, and study of bimolecular interaction. So see here, purification of histidine tag protein using a pH change. So you will see here it's so high, and then all of a sudden it just went down. Now size exclusion. So as I told you, it can be what? Gel formation or gel filtration. Okay. So here, this is based on a solid support that has center for size. So the way that you separate them, the smaller molecules will pass through the beads, while the bigger molecule will just flow, okay, outside the beads. So the question now, which comes out first, the bigger molecule or the smaller molecule? Okay, so if you're going to look at this, so this is how it looks like here. So if you have here the different what? Molecular weight, okay? So based on this one, when you do the separation, you separate this based on the size or molecular weight. So as solute travel through the support, small molecules can enter the pores while large molecules cannot. And since the large molecules sample a smaller volume of the column, they elute before the smaller molecules. So the one that comes after are the bigger molecules, and the one that elute later is the smaller molecules. Now they said there's really no true stationary phase here. Okay, the stagnant mobile phase, that's the one that acts as a stationary phase. But we could say maybe the beads that you have there, the agarose, Okay. So the name that I use, I think before is Cepadex, the gel Cepadex thing that we have the. So usually you use this for proteins and peptides, molecular weight determination. Okay. You're familiar with SDS page? May 161 na ba kayo? 161 pa rin ba yung biochem? Okay.
Dalawa po, 161A tsaka 161B.
Anong pagkakaiba? Lablet?
Hindi po, ang pinagkaiba po nun sir, hinati po kasi nila kasi kasama na daw po kasi yung biochem sa for the exam. So, ginawa po nila is carbohydrates, lipids sa A, yung B po is sa...
So dalawang sem na yung biochem? Kasi isang sem lang sa amin nun, 161. 160 is for the non-chemistry major. I see. Tapos meron pang graduate courses na ganun. Yung 261, 262, 260. Okay? Now, let's go with the detector. So if we're going to look at the detector, the more sensitive it is or the lower the detection limit, the more money that you need. Okay? So as you could see here, the best one, although it's not included here, it's the what? Mass spec. And there's a separate chapter of mass spec for that. So if you're going to look at the detector, okay, the GC will also have different detector. And it usually depends on the analyte. On the LC, this is based if you're going to use an analytical or preparative purposes. Okay? So anong different nung analytical sa preparative? Anyone? Have you heard the term before? Analytical versus preparative. So alin dyan for large scale purification? One of them is a small scale, while the other one is large scale. So the small scale is just for analysis purposes. The bigger scale is for purification purposes. Okay, so preparative is the one that is what? May sumagot. So usually yung preparative ang yung tinatawag nating larger scale. So if you want to separate or purify something, mas malaki din yung column na ginagamit niyo. Okay. We have that in my other lab. If we're going to look at the one that we have RI, UVB, fluorescence, conductivity, electrochemical, so they have their own selectivity and sensitivity. Okay. The one that we have there in UPLB when I was working is we have a refractive index. Okay. So if you're going to look at the refractive index, it looks at the difference between the signal coming from the solvent and your sample. So it measures the overall ability of the mobile phase and solute to refract or bend light. Okay. So it is non-destructive and they usually use it as a universal detector. Okay. Applicable to detection of any solute in the liquid. My experience there, I use it for sugar. Okay. Separation. It's applicable to preliminary liquid chromatography where the nature and properties of the solutes are unknown. Okay? Provided that it is, you have a concentration high enough. Kasi pag mababa, hindi niya madidetect. Ang disadvantage ito, hindi mo siya magagamit sa gradient. Why? Because the change in the solvent will also generate signal. So you don't know if the signal comes from the sample that you analyze or the change in the solvent na ano yung background niya. At Another disadvantage is it has a high limits of detection. So dapat mataas yung concentration ng sample mo for you to be able to analyze, to use this for analysis. So if you're going to look at the process here, so refractive index, so there's a light interaction. I-refract niya yung light. Okay, so the light from the source passes through flow cells containing either the sample stream or the reference stream. So when the refractive index is the same between the two cells, no bending of light occurs at the interface between the flow cells. But as the solute elutes, you're going to see a change in the refractive index between the reference and the sample cell. Because what happened, there's a bending of light. Light is bent as it passes through the flow cell interface. And the amount of light reaching the detector is decreased. Okay? So una solvent lang. So kapag naano na yung sample, mag-aano usually, mag-aano yung light mo. So magkakaroon ng decrease doon sa flow cell mo. And it will be detected on that thing. Now, UVB's absorbance detector is just similar with the UVB's, the spectrophotometer. Okay? So it measures the ability of the solute to absorb light at a particular wavelength. So this is another what we call common type of LC detector. If your sample can absorb, then you can use it. Now, the only thing that you need to know is you need to find what wavelength you have the maximum absorbance. Okay? So there are three common types of you have here, the fixed wavelength detector, the variable wavelength detector, and the photodiode detector. So the way that you look at this, okay? So you have a light source. Usually, kailangan talaga ng light source if you have this spectroscopic method. So in the light source that you have there, okay, it's going to interact with your sample. So you have here the light source. So it has this diffraction grating. Okay. So at a different wavelength, you can put there, you put your sample there. There's a flow cell side by side with the reference. And any difference that you have there, the UV source and the detector here. Okay, so that's where your sample pass through. So kapag may sample ka, usually mag-absorb yan at a certain wavelength. Like benzoic acid, it might, if I'm not mistaken, 240 to 260 caffeine at a much longer, higher concentration. Okay, so the way that you're going to do it is you can have the fix. So you set 254. So try to imagine spectronic 20 that is put in a chromatographic system. So kapag nagse-separate, nakikita nila kung may signal or may absorbance yung sample mo or wala. Okay? Now you can have a variable wavelength detector, or the one that is commonly used right now is the PDA. It simultaneously monitor your absorbance at different wavelengths. Yun nga lang, mas mahal to compared to that one. Okay? So the applications for this 254 for unsaturated organic compounds, 260 for nucleic acid, 280 for the proteins and peptides, taking advantage of the ring. Okay? Now you can use it with the gradient illusion. So this is the one advantage of UVBs compared to the RI. Pero mababa pa rin yung kanyang detection limit. Okay? Then the fluorescence detector. So you can only use this for what? Fluorescent sample. Okay? So this is just similar to a spectrophlorimeter. So pag nag-separate yung component mo, makikita yung detector kung present siya or hindi. Okay? So where it is applicable for those compounds that fluoresce. And then we have the conductivity detector. So here, this is applicable for ionic compounds. Okay? So usually what happened here is the presence of the ion would cause an out of balance signal that results that, oh, you detected something in your sample. Okay? So the detector measures the ability of the mobile phase to conduct a current when placed in a flow cell between two electrodes. And the current conducted within the cell will depend on the number and types of the ions present. So the more sample that you have, the more ions that you have, the higher the signal that you have. So meron kayong tinatawag na Wheatstone bridge. I don't know if you're familiar with this one. Usually we use it before in physics. Okay? So nangyari yan, meron ka dito, electrode, tapos dadaan dyan yung mobile phase. So kapag present yung ion, ma-out of balance yung signal mo. The more ions that you have, okay, the more signal that you can generate. So you can only use this for ionic compounds. Okay. But the thing is, you can also use this for gradient illusion. And this is much better LOD compared to the others. Now, the electrochemical detector, this is used for those that can undergo redox. Okay? So ito yung parang, yung electrochemistry naman, nilagay mo doon sa chromatography. So this is the good thing with the separation technique. Once you separate there, you can have a detector. And sometimes you can place what? More than one detector. As long as the first detector is what? Non-destructive. Pwede kang magkaroon ng yung relay of detector if you want. We use it, one that has the PDA, the absorbance, and the other one, yung tinatawag naming radioactive detector. So we try to detect the radioactivity. Okay? So the electrochemical detector, you can only use this for those that undergo redox reaction. Now, the limit of detection for this is, we could say, lower compared to the other. Okay? So I think that's it. Hindi ko na masasagot to. I can leave that to you. Okay, but we don't have anything to do for the what we call the next week. Bakasyon muna kayo. And then after that, saka kayo anuhin ng mga quiz. I'll give you maybe a take home when we come back. Calculation problem in chromatography. But for now, you enjoy your break. And I'm hoping that when you go to the cemetery, okay, you don't leave the motivation or the trust for knowledge doon sa cementerio. Okay? Question. Tanong. Ano yun? Kuha kayo ng feedback sa mga brad or sisters nyo na nag-board exam. Kung totoo ba, analytical yung what we call pinakamahirap because where is it? Oh, wala na yung yung note. Kasi kung totoo nga analytical, if you're going to look at the message that was shown there, tatawa ko yung pinakita yung yung message. Bakit na punta sa gaming yung ko? Ito. Oops, not that one. So if you're going to look at the thing that you have there, if you look at the comment, paasahin ka sa first 15 to 25 kasi puro Chem. So isipin mo kaya, pagdating sa last 75, di ko na alam kung saan nanggaling ang mga tanong. And sabi dito, I think may sinasabi yata na parang European. Yan, kakaibaan na Chem ngayon. Pang-European version ng calculation. Yeah, isipin nyo na lang, mahirap ang ng Chem. Kasi if you're going to look at the acronym, it's anal Chem. Di ba? So ano yung other words ng anal? Tatanggalin ko na yung recording.